Good morning, everyone. Thank you for joining us in our next installation of our Ask a Geologist web series. Today will be on volcanoes, presented by doctoral student Aidan Taylor. So a little bit about Aidan. He got his bachelor's from the University of London in geology, and he did his master's in mining engineering. And now he is studying volcanoes in Antarctica and also the tectonics of rift basins around the world. And he'll talk. Oh, someone's not muted. So that's a good reminder. Please mute your microphones. We will also check it for you, but please keep it muted while we're doing the presentation. If you have questions, please post those in the chat section. And please make sure you address it to all participants or the panelists so that we can make sure Aidan sees all of your questions. So without further ado, Aidan, it's all you. Thank you.
Okay. Good morning, all. Thank you for being with me this morning. At least we can make light of this quarantine sort of situation by doing great things like this with geology. So as Lauren said, my name's Aidan Taylor. I'm a Rutgers PhD student. I teach a few classes at Rutgers alongside the professors, and I'm a marathon runner. It's what I like to do in the spare time. It keeps the stress down. And I'm probably, if someone asked me to describe myself as a geologist, I'm probably best known as an exploration geologist, which means that I help companies find oil, minerals, metals, the sort of things that we need for crucial everyday life. And I've also been involved in geothermal exploration as well, which is when I worked with the Institute of Volcanology in the Canary Islands, which is in Volcan, which is what you can see on the screen there. And that's probably my closest connection to volcanoes outside of academia. And so geology is a great subject. So I've been to 5 of the 7 continents with work. It takes you all over the world. So if you are on the fence, if you have people you're trying to push into geology, or you have, relatives that are in geology sort of thing, it's a great career. You get to travel the world, do something very interesting. And at the end of the day, what's topical at the minute is things like climate change. And it's something that you get to study the earth, and you can have a huge impact on everyone's lives for the better. So what I personally do at Rutgers is I study magma chambers. So most of you know, sort of with this diagram on the right hand side here, your typical volcano sort of system. Okay, so you'll have a volcano, which is a pointy thing, which most of you know a volcano as, sitting on the surface. Okay. And then underneath that, you have magma, okay? So lava is the term that you give to molten rock that sits on the surface, and anything that's below the surface is magma, okay? And so what I research is the magma chamber down here. But most of you know that obviously we can't touch the magma chamber, okay? So I have to wait several million years or a long time, right, for erosion and weathering to bring this down to the present day surface. Okay, so if you imagine time 1 as your volcano, which is what you know today and see on the surface, and then once weathering and things start to erode this surface down, you start to get to the point where you're exposing the internal part of the volcano that once was lava or molten rock, okay? And then once that sort of solidifies, I can start to study it, because it's important for things like natural resources and minerals and metals that we need for everyday life. They're connected to some mass extinctions in the past. And of course, why everyone knows volcanoes is they're a danger to humans sometimes. And they can cause billions of dollars worth of damage. And I do this research with a range of institutes across America. And it's great fun. It's really rewarding. And it's why I do what I do. So volcanoes, right? Fundamental question, what is a volcano? And I think one of the questions that someone has already asked is, trying to find who it was that said it. Someone asked anyway, essentially, can a volcano be more than molten rock? And yes, it can be. So we usually give the term volcano to things like that you see on the news, okay? But they can be anything from mud to ice. It doesn't have to be molten rock that's coming out of the vent, so to speak. And so it's defined as really an opening in the Earth's crust where hot liquids and gases can reach the surface, okay, at a very basic scale. And so how do they form? It's typically where you have stresses in the crust, in the Earth's upper riding tectonic plate, okay, if you know what tectonic plates are, and it's where they're being pulled apart. So where they're being pulled apart, you usually get an upwelling maybe, and this magma then forms lava at the surface, which we know as a volcano. It can also be where you've got upwelling, so you don't have stresses being pulled apart. It's to do with subduction zones, which is where most people know volcanoes form, or to do with hotspots. Okay, so you all know Hawaii and Iceland and places like that. And typically they're mafic or felsic in composition. Okay, and don't worry too much about these terms. I'm just throwing them at you now because I'm just going to go through sort of some of the fundamentals as to how volcanoes form. And this, essentially, these two end-member compositions is what controls what type of volcano they go on to form. And essentially, don't worry about this chemistry, okay? I just want you to remember from these diagrams that from mafic to felsic, there is a chemical change, okay? And the most obvious one on there is SiO2, okay? Silica increases towards felsic, but don't get bogged down in this. All I want you to know from this is this plus the temperature of the magma is what controls a term called viscosity. And viscosity is essentially a material's resistance to flow. So you can think of this as toothpaste and water. So toothpaste, you've really got to get it to move, okay? You've got to put energy into it to get it to actually come out of the tube. Whereas water, we all know if you knock it over on your table, it will flow very easily. And so the difference between these two is sort of the difference between different types of magma. And it essentially controls how easily a gas can escape from a magma. And in turn, you can think of this like a Coca-Cola bottle when you shake it up and the gas can't get out. You know, once you take the lid off, it's going to explode, okay? And so this viscosity just controls the pressure. And so when you think about it with the two M members, sorry, Lauren? With the mafic and felsic.
Sorry, I'm here. Did you? I had to go grab a drink of water. Did you need?
Okay. No, I heard someone speak. So,
Okay.
mafic and felsic M members, with the low and high viscosity, as I said, it just controls the style of eruption. So, as I was saying, viscosity controls how easy the gas can escape. With this explosive style eruption, that's what you get here. And with an effusive eruption, the gas can kind of escape a bit more easily. So you end up with this shield volcano, which isn't exactly what most people think of when they think of a volcano. Most people think of this, right? And so that's the difference between why you get volcanoes that sometimes explode and sometimes you get volcanoes that are just...
video.
Sorry?
So just if you're coming in now, make sure your microphone is muted. We will occasionally check to mute your mics, but sorry, Aidan.
No, that's okay. And that's why sometimes you get volcanoes like this, which, you know, if lava is erupting towards you, things like Hawaii sometimes, and Italy maybe, there's volcanoes that you can sort of outrun the lava flow, okay? Whereas if you're presented with this, you really have to be, you know, aware to the dangers around you. And so where do they typically erupt, right? Most people know there's some volcanoes in North America. And then, of course, from the news, you hear about certain volcanoes, say Indonesia, places like that. And so volcanoes are actually constantly erupting. They're always erupting. And so most of these are along the seafloor. Okay, so that's what you can see on the left-hand side here. But due to plate tectonics, so essentially the ground that we stand on is always moving because we stand on what's called tectonic plates. And these tectonic plates control certain volcanism, certain volcanoes that form around the world. And so you can see here with the outline of where I'm tracing the mouse, this is the Pacific plate, and this is the Ring of Fire, okay? And that's mainly because around the Pacific Rim, around the Ring of Fire, most of the contact zones between two different tectonic plates are actually subduction zones. And so what they actually look like, taking North America as an example, is in the Cascades in the Pacific Northwest, you can see that you have a tectonic plate going underneath another one. And what happens when this happens is the plate essentially melts, okay? And it forms volcanoes above where it's melting. And so that's why you have a lot of volcanoes where you have subduction zones. And you can also get volcanism at the middle of the ocean, as I was saying, where you get these mid-ocean ridges, as well as hotspot zones, okay? So Hawaii and Iceland, places like that, you get an upwelling of hot mantle. So essentially the more sort of plasticky stuff that sits underneath the crust that we stand on. And then it can erupt at the surface. And this doesn't have to be at the edge of a plate. So they can erupt pretty much anywhere on the surface, which is pretty scary, right? But typically, volcanoes typically occur at the edge of plates. And so a great resource for this is the Smithsonian Institute sort of weekly activity report. So it gives you all the volcanoes that are sort of erupting this week or today, sort of thing. And as you can see, the Ring of Fire is very active. It's most of what's going on at the minute today. And so if you want to check this out, the resources are at the end. So eruption styles, as I say, you get things that sometimes you can outrun. They're pretty slow. You can run away from them, and sometimes you have an explosive eruption that you really have to be on top of or be aware of beforehand. And so there's multiple classification schemes to go through different volcanic eruptions, but I'm just going to show you the volcanic explosivity index. And it's measured from 0 to 8. And the things that go into it are things like how high is the column of ash and molten rock that gets thrown up into the air, as opposed to how much kinetic energy is in there, how much energy is released when the eruption happens, and the volume of material that gets erupted. And so with the eruption styles, the lowest part of this is really considered common on human timescales, okay? These are things that happen daily to, once a year sort of events. They're very common, what you'd say in our sort of lifetime. And typically there's no column associated with these, but they can have pretty big eruptions sometimes. As you can see from the Soufriere Hills volcanoes on Montserrat, when this erupted in 1995, it sort of did what most people know happened with Vesuvius. There was a pyroclastic flow that came down the side of the mountain and engulfed a lot of the town. And so these volcanoes can still be pretty dangerous on the common sort of timescales. But there's also things like fissures that you see in Etna and Iceland sometimes when volcanoes erupt there. And they're just very linear, effusive eruptions that can have a lava fountain, right? But they're nothing sort of to worry about as far as immediate danger to life, okay? But they are very dangerous still sometimes. And then there's the ones that grab the news headline, okay? The ones that we all typically know about. These are the 5 to 6, the VEI 5 to 6. And these occur on every decade to century sort of timescales, and there is usually a loss of life and billions worth of damage associated with these. There's long-term impacts like the impact climate because of the gases that they give off, as well as long-term impacts in the sense of you don't really think it, but things like ashfall, as this diagram is showing here, falls out of the column, and then that can rain down on people's houses. And when that accumulates after a while, people's houses start to collapse because there's so much weight on top of the houses. And there's just all these sorts of things that people don't realize, that the main eruption is terrible, but there's a long-term impact afterwards as well. And then you go up to the VE7, which is the ones that we have very little knowledge of. The one that we do know of is Tambora in 1815. There's previous eruptions, so like Mount Mazama and things like that, which we're not sort of sure whether like sort of we have accurate representations of those things. But the one thing we do sort of have an accurate representation of, which is in recorded human history, is Tambora and the year without a summer. Okay, so VI7 eruptions are huge. These are caldera forming events, which basically means the magma chamber is essentially thrown up into the air. Okay, and these happen very rarely. Along with VEI8 supervolcanoes, which most people know, Yellowstone, these are, hundreds of thousands a year events. These are really rare, but when they do happen, they're huge. But most people hear about the 5s and the 6s. Okay? And so this kind of leads to the question, do we know when they all erupt? And the short answer is no. And a geologist should never really give this away, because a lot of people who don't understand geology want a definite answer. And geologists and volcanologists, same with earthquakes, we can't really give a definitive answer as to when things are going to happen. But we do have clues. And so things like gas emissions, so a spike in SO2 emissions, earthquakes, which show that there's magma moving underground, as well as GPS data. But there's no crystal ball. But we did use these things effectively with Mount St. Helens in 1980. So we saw a spike in SO2, but the big giveaway really was the GPS data, which noticed that the side of the mountain was starting to bulge, which is what you can see over here. And so it was a series of earthquakes, and the GPS data told the scientists at the time that the side of the mountain was bulging outwards. And that eventually led to a flank eruption, which was terrible. 1980 was it was one of the biggest eruptions we've seen in North America. Okay, and one of the questions was, what is the threat probably to North America at the minute as far as volcanoes? And Yellowstone is obviously a huge one, but it's not really an event that is likely to happen. Okay, but if you think of Pacific Northwest, Mount Rainier, all these volcanoes up there, like Mount St. Helens, these are the big ones that could have a devastating impact on places like Washington. And so why study them? It's obviously fun, right? But there's huge implications as far as, looking after humans, making sure everyone's safe. They cause a lot of damage, and they can have an impact on climate. But one of the things I was involved with down here in the Canary Islands was they could provide geothermal energy to people, okay? So we can use the heat to boil water, essentially, and that steam can drive turbines, okay? They also disrupt flights. So Eyjafjallajökull, when it went up in 2010, the Icelandic volcano, shut down Europe for like a week. We've seen from the pandemic how how much damage that can cause the airline industry. This is another one of those. So, and also to study the Earth's interior. We don't get many opportunities to actually look inside the Earth. And so we can learn something about the Earth by studying volcanoes, as well as other planets like Olympus Mons on Mars. Okay? And so there's just a few nice resources there. We can make those available to you. This top one is the Smithsonian Institute one that I just showed you, as well as the Daily Motion, which is a BBC documentary about the volcano in Africa. And it's a really good documentary. It shows you the socio-economic impacts as well as sort of the geohazards associated with volcanoes. So with that, I'll sort of answer your questions now. So if you do have any questions, please put them into the chat, and then the guys will put it online, and I'll be able to check it on my screen here. So the first one here is, the first two is sort of covering how did volcanoes form and what caused them to erupt. So I've sort of gone over that, as well as the Ring of Fire. And so one of the most realistic volcanic threats facing the US is, as I say, probably in the Pacific Northwest, where the plate is still subducting under North America. And you get these subductions on volcanoes, which are very explosive and can cause great damage. And so I've had a lot of questions as well about basalt and cooling into the sort of the cooling sort of joints that you see in like the Giant's Causeway, as well as a lot of other places around the world. And really, I'm not actually 100% sure as to how that forms mechanically. It's to do with the stresses, but the main sort of parameter with cooling joints is the fact that it's rapid cooling. Okay, so it happens very quickly, whereas magma chambers are allowed a very long time to cool. So you don't get so many joints in a magma chamber because they're given a long time to cool. whereas when you get dikes and sills, sort of at shallow levels of emplacement, you get the cooling joints because they cool very quickly. So one of the questions is, out on a hike from Zayden in Roxbury, out on a hike you found a very black, shiny, lightweight rock. And so it probably looked something similar to this, okay? And this is obsidian. This is a glass that's formed when lava is essentially given 0 time to cool. So it forms a glass instead of crystals. And so this is probably erupted into water, let's say, because it's quenched straight away. But what you've probably found actually, because obsidian is very rare, especially in New Jersey, it can be quite rare, is what they call slag, okay? And slag is essentially, it's a ballast of boats because it was used in the manufacture of smelting process, and it can form glass, okay? And it can form black glass, so it's very light. Typically with obsidian, it's heavy, okay? So if you found it and it's light, it's probably slag from the Boss process, and it's been thrown off ships, which was ballast when they were in New Jersey, and then it finds its way onto the land just through processes, geographical processes. Tyler from Halifax in Massachusetts said, your friend gave you a lava rock in Hawaii and it has holes. It's probably a little something like this, okay? Probably a little. Yep. If it looks a bit like that, it is real. It's basalt. It's what you call either scoria, if it has a welded texture, or it's vesicular basalt, which just basically means that the gas bubbles, as I was saying at the start of the lecture, don't really have time to escape. And so it leaves holes within the rock where gas was. And when it cools down like that and gets eroded and weathered, it forms very like sort of ashy, holy sort of rock.
Hey, Aidan, you can stop sharing your screen so that if you're going to show a rock, they can see a bigger
Okay.
picture.
Okay, so you got me full screen now, Lauren. So how hot can a volcano be? Lava is typically 1,300 to 1,200, 100, okay? And this temperature, as I was saying at the start of the talk as well, sort of controls viscosity. So you get different lava types as well, depending on that viscosity. So it's around the 1,200 range if you're going to give an average. But magma itself, when it's under the surface, can be a lot hotter than that. But yeah, a lava on the surface is typically 1,200. So you've also got questions about how you get shield volcanoes and how they can form very big volcanoes. Okay, so essentially, when you get stratovolcano, which is the big pointy ones that you usually sort of see in the literature and things like that, those are the way they are because of as I was saying, they are highly viscous. Okay, so they have a very high resistance to flow, which means that they don't travel very far. And a lot of the material that they eject gets dumped essentially right on the side of the vent, on the side of the volcano. So if you imagine this as it is, then you have ash falling down here, which builds up the volcano, as well as lava flows that are very sticky and don't go very far. And then they tend to build up a stratovolcano like this. Okay, so you have a very steep sort of angled large mountain, right? And then if you think of shield volcanoes, they're very like low, okay, very gentle sloped. And this is again because of the viscosity. So it's essentially the fact that their lava flows can flow for miles. And so they eventually just build up and build up and build up layers of lava that flow for a very long distance, and they end up with this which is why it's called a shield. Essentially, it's just a very gently shallow volcano, rather than a very pointy one, which is the typical sort of thing that most people think of. And so that shield volcano, it can actually be very big. Mauna Loa in Hawaii is huge, okay? And from the base of the volcano to the very top, it's actually one of the tallest structures, natural structures on Earth. And so, yeah, that's how sort of shield volcanoes differ from the typical sort of pointy stratovolcano. How long does it take for a volcano to form? That's a good question. It's usually millions of years. So if you think of places like hotspots, usually they can form in a couple 100,000 years, as far as sort of getting up from the ocean bed, so building material to reach the surface. But if you're talking sort of like long term in geological time, you're sort of thinking on the scale of at least 1 million years if you're thinking a hotspot sort of thing. And then the hotspot trail you'll see will go out several million years. With subduction volcanoes, I don't actually know what the time is from sort of initial subduction to starting to form volcanoes. And divergent margins, or sort of part in the ocean where plates are being pulled apart. Again, that's a sort of tectonic thing that can take a process of tens of million years to start to rift apart to then actually produce volcanic material. But hotspots are usually the quickest way to form a volcano. The biggest volcano, as I say, from sort of bottom to top, is Mauna Loa in Hawaii. But as far as like material, one of the largest volcanoes is Tamu Massif, okay? And that's 2.5 million cubic kilometers, which is a huge amount of material to be erupted. How does plate tectonics work? Okay, Amy Clapp from Salisbury, Vermont. Tune into Chris Rowan's lecture in I think next week. Lauren, when is Chris giving his lecture?
It's not next week, but hold on, I have to. You can go to the next one, and I'll look up the.
Yeah, sure. But Amy, Chris is going over that, so I'm not going to steal his thunder there. But essentially, plate tectonics is sort of what controls volcanoes and earthquakes at a very fundamental scale. But Chris will be going over that.
It's April 14th is when he's giving it. Yep, at 11 a.m. on April 14th will be the one about plate tectonics.
Cool. So Amy also asked about hotspot volcanoes. So hotspots are just, it's not actually fully understood how they actually form. Theory is they sort of come from the core mantle boundary, and then they sort of float up. They don't float up, but they upwell due to being hotter than everything around it, up towards the crust, and then they punch through the crust and form a volcano at the surface. But yeah, what causes a hotspot? It's not actually 100% understood in geology. Not at least can be explained very simply. The one that buried Pompeii, Mount Vesuvius, was a VEI 5. So just to give you an idea of that, it might have been a VEI 5, VEI 6, but it was a big eruption. And yeah, it just gives you an idea of the fact that that wasn't a VEI 7 or 8, and it caused that much damage and loss of life. It was catastrophic. So yeah, that just gives you an idea of how powerful these VEI 5 or 6s are. Good question, Leela. So calderas are different from a normal crater in the sense of it's, rather than it being sort of a pointy cone, right, a stratovolcano, where you get ejecta coming out of the top, out of the main vent, or out of the side of the volcano. but it's to do with the main structure, okay, the main conduit, the edifice of the volcano, the stratovolcano, okay. Whereas a caldera is where actually the magma chamber that feeds it underneath actually collapses. So you have the crust, it collapses in on itself, and when it does that, the magma chamber essentially is evacuated into the air. And so that's how typically most caldera forming eruptions happen. And so it's a huge eruption. It's the VEI 7-8 sort of scale. And so these differ in the sense of it's the whole system sort of exploding at once, as opposed to a smaller stratovolcano. And then you can also get what they call resurgent volcanoes, where once that's happened and it's been evacuated and time, millions of years pass, you can have the caldera sit where it is, and then you get another cone start to form within that sort of bowl that's left behind where the caldera is. Good question, Lily. You also asked about how do volcanoes alter climate. And so volcanoes alter climate by the gases that they give off, which, as far as gases that they give off, I don't know the exact numbers, but on an annual basis, it's not really enough to alter climate as far as continuous eruptions and sort of ongoing just effusive emissions. It's more the large events, so the VEI 6s, 5s, 7s, and 8s that alter climate when they happen. And it's to do with, we all know what CO2 is. It's a greenhouse gas that traps the heat within the earth. And essentially, when volcanoes go off, they release a lot of CO2. And so on a long-term scale, volcanoes can cause warming of the planet. But on a very short scale, they also emit SO2. And SO2, as I was saying earlier, is the one that's sort of the warning gas for when a volcano is going to erupt. But it also, when it's erupted in large volumes, like it is in a large eruption, actually cools the climate on a very short-term basis. So as I said with Tambora in 1815, it actually produced a year without a summer because the amount of SO2 that was released was enough to actually cool down the planet such that a season completely vanished, right, within records. But it's the gases that are erupted from a volcano that alter the climate. So, sorry, Miriam, you said, can you explain again what starts a volcano? So essentially it's to do with either a stress, so where in the sort of ground that we stand on today, whether you get stresses pull it apart, and it allows the mantle or the molten rock essentially underneath that sits underneath where we are on the crust to come up towards the surface. And so it comes up through cracks and openings in the surface. Or it's to do with plate tectonics, where you get subduction zones. So you get plates starting to melt at depth that then form a volcano above where it's melting. Or you get hotspots come up. So again, most of it's to do with heat in the mantle, okay? And so when it comes up, it hits the crust and then punches through and forms a volcano where that hotspot comes through. But typically it's the very basic way to describe it is it's an opening or crack that forms in the crust that allows material to come up through the crust from the mantle. So a good question here, and my diligent colleagues who are writing down your questions have answered it for me, and I would have no idea unless they've answered it for me. They said, how many supervolcanoes have been reported in history? And apparently there are 60 supervolcano eruptions in history, but there are only 6 supervolcanoes that we know of today. Supervolcanoes, the one that most of us have heard of is Yellowstone. There's various other ones. One in Italy, which is, I can't pronounce it, Campi Fleri or something like that. is another one that sits under Italy, and that's actually another supervolcano that we're very aware of, and is probably talked about in the same light as far as likelihood of eruption with sort of Yellowstone, as well as various others around the world. But supervolcanoes are not really something too many people should be worried about. Another good question. Daniela. So Daniela said, is there a relationship between geomorphology of a volcano and its chemical composition? So the geomorphology goes back to how I was saying with if you have a felsic volcano, so a high viscosity volcano, you start to get the cones forming because they don't transport material very far. As opposed to the shield volcanoes, which are very shallow, think Hawaii, right? And those are large and like that because their lava that gets erupted can flow for a very long distance, and that is controlled by their chemical composition. Another interesting thing to think about as far as geomorphology as a volcano and its chemical composition is more for the geomorphology sort of side, which is if a volcano underlies a glacier, for example, or the ocean. When it erupts as something called a phreatic or phreatomagmatic eruption. And essentially what that means is it's a combination of steam and volcanic glass, okay, as well as volcanic material. But essentially what you're projecting then into the atmosphere is very, very fine particles of rock, okay, which differs from a typical eruption because they're just so much smaller. And these are the reasons why you get volcanoes shut down airspace a lot of the time, because they are a danger to sort of jet engine aircraft. And so that's another thing to think about as far as like sort of subglacial eruptions and things like that with geomorphology, that the geomorphology of the landscape can vastly affect sort of the eruption style as well. What inspired me to study volcanoes? I think primarily it was probably I went to the East African Rift Valley when I was in college. College meaning high school to you guys. And when I went there, I was fascinated by the East African Rift Valley, which is why I've always been sort of interested in sort of rift tectonics and volcanoes, as well as, you know, as any kid who grows up interested about volcanoes and earthquakes, and sort of, you know, understanding them and sort of having, you know, a better impact on society, which is primarily one of the reasons why I started to study them. Most active volcano in the world is Kilauea. I have also never been to Antarctica. So the samples that I got were from the Polar Repository at Ohio State University. So I've actually never been to Antarctica, but I study the rocks that came from there essentially, and were collected in like 1960, a very long time ago. Good question, Jake. So meteorite impacts can cause volcanic eruptions, but they are not the typical style of eruption, okay? Typically, they will be so large that they puncture the crust, and so it's kind of a weird question because a lot of the stuff can be metamorphic as well. But yeah, they can cause volcanic eruptions, but it's more so the fact that it melts everything that it sort of touches because it's the intensity of the impact is so hot. And that's where you get melt breccias and stuff like that, as opposed to typical lava, because the chemistry that's involved in the sort of impact isn't typical of volcanic eruptions, sort of thing. But yeah, it's a good question. Okay, good question from Ria's mum, Tanu. So lava can flow through a tube again. So lava tubes are these things that are like subterranean networks by a volcano. So if you have a lava flow that comes through and then sort of has a hard top, and then you get continuous lava flows on top of that, it can form a crust, and then underneath it is very hot molten lava. And it's flowing. And so after a while, you get these tubes start to form where you have essentially a subterranean network of tunnels of flowing lava, but on the surface, you can't see those tubes underneath. And so when eruptions happen, they can revisit the same tubes. And why is tourism encouraged at active volcanoes right after eruption? Good question. I suppose because a lot of people want to go straight after an eruption, but I agree with you. It's not necessarily a wise thing because it's the same as sort of hiking on a glacier with crevasses in spring. You don't know where these lava tubes are, and it's a dangerous business to try and work out where they are. So you have to be very careful with these things, especially when you're going into these lava tubes and there's no eruption ongoing as well. They can be very dangerous then, because you also get collapses within these lava tubes. They're not very stable things. So yeah, lava tubes can be pretty dangerous, but they're obviously spectacular, and it gets the wanderlust that's in all of us. So there have been volcanoes on the East Coast. The White Mountains are an example of past volcanoes on the East Coast, but there's no subduction happening on the East Coast anymore. There was several millions of years ago, but there's not anymore. So no volcanoes on the eastern side of America at the moment. So good question. How can volcanoes be involved in the formation of mineral deposits? So volcanoes are made up of X amount of chemistry, okay? And within that chemistry, there are trace elements of certain minerals. So let's say there's gold in there, there's copper, things like that, but in very small amounts. And so when you get eruptions, essentially you're leaving behind this magma chamber. And in this magma chamber, it's convecting. And with continuous pulses of magma into the magma chamber, it builds up to build a big magma chamber, okay? And then within that, there's something that's a process called fractional crystallization. And you don't need to know too much about that other than it separates melt from other bits of melt, okay? And what this process does is it can enrich. If it's in a very fine proportion in one melt, if you keep increasing it by essentially diluting or concentrating, right? You can then enrich the amount of metal that's in one of these magma chambers. And then there can be processes that happen afterwards. So fluids might come in. So fluids like water, hydrothermal fluids can come in, and they're bearing these same minerals or metals. And they can in turn enrich these metals or minerals in the magma chamber itself as well. So it's essentially a process of concentration, to the point where you go from having a magma that's typical magma, you know, the sort of thing that we recognize as rock, okay, until you start to enrich it in minerals that we need for everyday life. A good question is there any way we can stop volcanoes? Not really. We've all seen films where they've tried. I think the biggest tool we have in our asset really is in our war chest as far as sort of trying to control volcanoes is the mitigation for a start. So as I said, using the tools to make sure that we know when an eruption is going to happen, or at least can guess when an eruption is going to happen. We can not build houses on the side of mountains where there are volcanoes. That's a first. And then when there is lava like erupting and it's not an explosive eruption, there are reports of people. So there's one in Iceland where a volcano was sort of about to destroy the harbor, which, you know, in Iceland, a lot of their trade is through fishing. And so it was imperative that they stop the lava flow. And so they redirected the lava flow around the harbour. And so you can kind of do it with, just brute force of sticking things in the way of the lava flow, and, cooling it down quicker. So putting water on it, etc., which, in a place like Iceland, if you're by the coast, you have access to plentiful water. And so you can cool it down to the point where it solidifies enough that it becomes a barrier, essentially, to the rest of the flow. And then it will take the path of least resistance. So there's no way we can really stop volcanoes, but there is kind of a way with lava that you can sort of deflect it almost. But you're never really going to stop volcanoes or stop them erupting to start with, which is one of the reasons we have to take them so seriously. Okay, starting to run out of questions, guys. I
think that was all the questions. Are there any other that? Oh, someone just asked, what is a flood basalt?
Okay, so flood basalt. Flood basalts are essentially that very shallow volcano, okay, where lava can flow for like very long periods of time, okay, and over great distances. But flood basalts are like sort of eruptions in Earth's history where you get massive amounts of volume of erupted material. And it's usually that effusive stuff, but it can be explosive as well. And the flood basalts are usually also coined a different name, which is called large igneous provinces. And essentially, it just means that in a very, very short period of time, you're talking several hundreds of thousands of years, there is a huge volume of lava erupted. And this can cover massive sort of like areas. So if you think of sort of the Northeast America, okay, there's a flood basalt or a large igneous province called Camp, which is the Central Atlantic Magmatic Province. And so essentially this outpouring of lava was such that it actually stretches all the way from sort of North Carolina down near Florida, all the way up to sort of Nova Scotia. And, this magmatic province then ends up being, with rifting that happens as Europe has come away from North America, you've ended up with the North Atlantic province up there, which is a magmatic flood basalt as well. And so, you can think of this as flood basalts. There's several around the world. There's multiple ones, but they cover a vast majority of the surface when they do erupt. And if you Google sort of large igneous province, you can see all the ones that come up and all the different ages. And they've come up throughout Earth's history at random times. Often, usually, people associate them with hotspots, which, there's a lot of literature out there that goes for that, and there's a lot of literature that goes against that. But yeah, flood basalts are really interesting. And those are the things that also are typically associated with mass extinctions as well, which isn't always correct, but there might be some theory behind it, which is the fact that because there's so much volume of magma erupted, there's also a massive amount of gas emissions with that. And as I was saying with climate, if you put so much CO2 into the atmosphere, you're going to sort of warm the climate. And so there is an association with flood basalts and warming climate and sort of mass extinctions. But the link is in various parts of Earth's history, not 100% concrete. But there are, sort of these flood basalts that can alter the biology of the planet. These are the questions again. So one of the questions is, if you could study any volcano, which one would you study? And for me, it would be Eyjafjallajökull in Iceland, just because I was studying volcanology at the time that it erupted and closed down airspace in Europe. So I just have a strong connection with the fact that it was a volcano that erupted when I was actually studying volcanology at my undergrad. And it's just a really interesting volcano because it's a very rare style of volcanism which produces, as I said, this very fine ash because it erupts underneath a glacier. And it was also interesting because the eruption produced mafic and felsic volcanism from two different style of events, which is why you had sort of a smaller eruption and a greater eruption at a different time. How many volcanoes are there in the world? There are 1,500 potentially active volcanoes in the world. Of these, 500 have erupted in historical time. Again, thank you to my colleagues who are working away diligently in the background, because again, I wouldn't have known that. So yeah, the 500 in historical time, but there's a lot of volcanoes, as I say, and they are constantly erupting under places like the seafloor. Good question. So can we get explosive eruptions from a mid-ocean ridge? The answer to that is I don't know, but I would be 90% sure that you can't. I think most mid-ocean ridge eruptions really kind of happen because there's either a pressure buildup or, you know, there might be a contact with water, which is what you see in that little GIF that I had in, and that can kind of give the impression that it's an explosive eruption. But in general terms of volcanism, it's not very explosive. So yeah, I'm 90% certain there's not really an evidence of sort of explosive eruptions at a mid-ocean ridge, unless you then team it with a hotspot. So Iceland sits on a mid-ocean ridge, and so you have explosive volcanism there from every so often. But typically at a typical mid-ocean ridge, there's not really explosive volcanism.
Yeah, I think that was all. Are there any other questions, panelists? I don't see any other ones, but this is great. So Aidan, I'll let you sign off. You can say goodbye.
Okay.
And then, yeah, thanks for everyone for joining us.
Yeah, thank you guys. Thanks for all being here today.
Yes, it's great. So be sure to join us on Thursday. We will be talking with Dr. Rhonda Quinn, who will be discussing human evolution with us. So thank you, everyone, and we'll see you on Thursday.